This is stochastic processes module 8 renewal processes. In the model 1 we have presented the probability review and introduction to stochastic processes. In the model 2 we have presented the definition of stochastic process and its properties. Stationary processes is discussed in model 3. Discrete time Markov chain is discussed in module 4. Continuous time Markov chain is discussed in module 5. Martingales are presented in module 6. Brownian motion and its properties are discussed in module 7. Now we are giving the presentation on module 8 renewal processes. In this we are planning to give lecture for 5 hours, starting with renewal function and the renewal equation in the lecture 1, generalized renewal processes and renewal limiting theorems in lecture 2, and in the lecture 3 we are planning to present a semi-Markov process or Markov renewal process and Markov regenerative process. And in the lecture 4 we are planning to present non-Markovian queues. In the lecture 5 we are planning to present non-Markovian queues with respect to the service distribution. In this lecture we are planning to give the definition of a renewal process and the related properties. Then we are going to present a renewal equation, and then we are going to present renewal times. Then finally we are going to explain what is the meaning of age, excess and the spread at time t. The renewal theory is the branch of probability theory that generalizes Poisson processes for arbitrary inter-arrival or holding times. Renewal, as the word suggests, means that an event occur again. In this, when we say that x1 is the time of first renewal, then it refers to the first time an event occurs, where event may be defined as required by the user. Let x1 be the time to the first renewal, and let xn, n running from 2, 3 and so on, be the time between n minus 1th renewal and nth renewal. Assume that xi's are independent, identically distributed random variables with the distribution function capital F. The mean for the random variable xn, that is denoted by the mu, that is nothing but 0 to infinity x times integration with respect to df of x, which will be positive because xi's are nothing but the time between the n plus 1th arrival to the nth arrival, that is a random variable xn. Hence the mean will be a positive. Define the time of nth renewal by Sn is a summation of first xi random variables. The xi's are nothing but the time interval between the I minus 1th renewal to the ith renewal, and Sn is nothing but the time of nth renewal, that is denoted by summation I is equal to 1 to n xi. So for every n you will get a one random variable Sn. So S1, S2, S3 and so on. So this is the time of nth renewal. That's a collection of random variables. The another random variable, let nt be the number of renewals by time t. So that n of t is the maximum of n such that Sn is less than or equal to t. That is nothing but how many renewals takes place on or before time t, that will be the random variable n of t. So one can relate nt with Sn with this formula, maximum of n such that Sn is less than or equal to t. So the n of t is nothing but counting how many arrivals, how many renewals takes place till time t. Therefore, this is a counting process, and this counting process will be a renewal process. If for some n Sn is equal to t, that means a renewal is said to occur at time t, or Sn gives the time of nth renewal and is called the nth renewal time. Sn is equal to t, that is nothing but the nth renewal time. Let us see the sample path of a renewal process. In this sample path of renewal process, the x-axis has the renewal time points. Renewal time S1 is the first renewal, the time in which the first renewal takes place. S2 is the time in which the second renewal takes place. S3 is the time in which the second renewal takes place. The x1 is the time between the first renewal and the second renewal. The x2 is the time between second renewal and the first renewal. And xi is nothing but the IID random variables with the distribution function capital F of x. Since it is a in between the renewal time between the renewal time, therefore the mean will be a positive. So in this sample path we are giving the different values of x1, x2, x3, and what are all the different time points in which the renewal takes place, that is S1, S2, S3, S4, S5 and so on. And in the y-axis we are making a count n of t. So till some time the renewal is only 1, after sometimes the renewal is 2. So suppose you stopped it somewhere and asking how many arrivals takes place at this much time. Therefore 2 arrivals takes place at this much time. After crossing, suppose I stopped it here, then there are 4 arrival takes place at this much time. Therefore the n of t is equal to maximum of n such that Sn is less than or equal to n, Sn is less than or equal to t, makes the possible values of n of t. So n of t for possible values of t, that will be a stochastic process, it is a counting process, and this is a renewal process also. And xi's are the IID random variables, and Sn is the time of nth renewal. A common feature is this example thus is that rather than studying a random value of a sum of fixed number of random variables, one investigates the random number of terms required in order for the sum to attain a certain deterministic value. For non-negative summons, we are lead to the part of probability theory called the renewal theory, and the summation process Sn is called the renewal process. So this is the connection between the random walk and the renewal process. Now we are moving into the remarks of a renewal process. The first remark, a counting process for which the inter-arrival times are IID random variables with arbitrary distribution is said to be a renewal process. Whenever you have a counting process in which inter-arrival times are IID random variables with whatever be the distribution, with the arbitrary distribution, is said to be a renewal process. Second remark, a Poisson process can be defined as a counting process for which the inter-arrival times are IID with the exponential distribution. So the Poisson process is a special case of a renewal process in which the inter-arrival times are exponential distribution. IID as well as each has exponential distribution. Identical, independent and identically distributed random variable. A renewal process is more general counting process than Poisson process. A renewal process is more general counting process than Poisson process, because in the Poisson process the inter-arrival times are identical, independent and each one is exponential distribution, whereas in the renewal process it could be any arbitrary distribution. Any counting process need not be particularly Poisson process. A continuous time, third remark, a continuous time stochastic process in which the embedded jump chain, that is nothing but the discrete process registered what values the process takes, is a Markov chain, and where the holding times, that is nothing but the time between jumps, are random variables with any distribution whose distribution function may depend on the two states between which the move is made. We say it is a semi-Markov process or Markov renewal process. If this condition is satisfied by a continuous time stochastic process, it has the embedded Markov chain and the holding times depends, it can be any distribution, but it depends on the two states between the system moves, then the corresponding stochastic process is called a Markov renewal process or semi-Markov process. We are going to discuss the Markov renewal process or semi-Markov process in lecture 3 in detail, and the application of semi-Markov processes in queuing models will be discussed in lecture 4 and 5. The remark number 4, when the probability of x takes the value some constant c is equal to 1 for some constant c greater than 0, then the corresponding renewal process is called a deterministic renewal process. This x is nothing but the inter-arrival time. For renewal process, the inter-arrival times are IID random variables. Therefore, for one random variable, we are defining it's a constant random variable. If these IID random variables are constant random variable for some constant c greater than 0, then the corresponding renewal process is called a deterministic renewal process.